Okay, Chapter 9, Worksheet number 5. We have a wrench with a 50-pound force being applied to it here at the end. We're told to determine the principal stress and maximum in-plane shear stress at point B here on the cross-section of the wrench at section AA. Then we're told to specify the orientation of these states of stress and indicate the results on elements at the point. So digesting that, we're finding our principal stresses, sigma 1 and 2, and our max in-plane shear stress, and their associated orientations, and draw the elements. Right, we're given a 3D rigid body and a circular cross-section where we're cutting through. So our solution, we first need to do our combined loadings, our stress analysis in that way, where we're looking at our free body diagram to find our internal resultants, to find the state of stress at B. Okay, that's everything up till chapter 8. And then chapter 9 stuff, we're going to use Mohr Circle to find our principal stresses, our max in-plane shear stress, and our angles. So same process as our previous problem. We just have a different rigid body with a different type of force. We're going to have different internal resultants, but same kind of process. So our statics part, our free body diagram here, this 50-pound force is going to cause 3 different resultant reactions here at our cross-section. Out of our 6 possible reactions, right? We have 3 potential reaction forces, 1 in each direction, and then 3 potential moment reactions, 1 about each axis. So we don't have an axial normal force, that would be in the x direction, from how we drew our axes here, a transverse shear in the z direction, or a bending moment about the y-axis. But then we will have a shear force reaction in the y direction, a moment about the x-axis, which we'll call our torque, and a moment about the z-axis, which will be a bending moment. So I had the bar here be the x-axis, y-axis is here, so this is our z-axis by our right-hand rule. So our first resultant is the shear force in the y direction. And that's going to be going in the negative y direction to oppose this 50 pounds. And then we're going to have a moment about the x-axis, which is what we're going to call a torque, because it's a moment about the longitudinal axis that we're cutting through. So that's Tx, and that Tx is going to be the 50 pounds times this z moment arm, force in the y direction, times a z moment arm, gives us a moment about the x-axis. And that's going to be a negative 600 because the way I drew it here, the torque needs to be going in the opposite direction. This 50 pounds is going to cause a rotation around like this. So we need to have a torque that causes a rotation in the opposite direction. So our thumb should be pointing up toward the pipe. So these double arrows need to be going up. That's why we got a negative. Our final internal resultant is going to be our moment about the z-axis. That's because this force has this x moment arm. Y force times the x moment arm causes a moment about the z-axis. And this is the proper direction for the resultant because the 50 pounds is going to cause a rotation around like this. So then for equilibrium, we need a reaction moment going around like this. Put your thumb in the direction of the double arrows and curl your fingers using your right hand. And that moment's going to be 100 pound-inches. All right, so that's our statics. Now we have to do our mechanics materials part where we use our flexure formula for our bending. And at point B, this bending stress is going to be maximum because we're our furthest distance away from our neutral axis, the axis that we're bending about, which is the z-axis here. And if we're looking up at the cross-section with our axes oriented this way, we can see that that moment is going to cause compression at point B, and it's going to be maximum because we're at our furthest distance away from that neutral axis. So bending stress will be maximum and compressive at B due to our moment about the z-axis. Then you just have to plug in your values into your flexure formula. Our MZ was 100 pound-inches. The negative sign is accounting for the fact that it's going to be compressive. You can just use this kind of sign convention. And then our distance from the neutral axis to our point is our radius, so 0.5 inches. And then our I for a circular cross-section is pi over 4 times r to the 4th. Calculate that, and you get our normal stress at B is a negative 1.019 KSI. And the face that we cut through has an x-axis coming out of it, so that normal stress is going to be sigma x at point B. If we were to cut through, say here, for instance, our normal stress would be in the z direction, but we're cutting through here, x-axis is coming out, that's in sigma x. And a note here that we don't have an axial normal stress, right? We only had these three internal resultants, so there's nothing for it to combine with. This is our only normal stress at point B. Now again, looking at our cross-section, we can determine that our transverse shear is going to be 0 at point B, because our Q in our shear formula from VQ over IT is going to be 0 because the A prime value of Q, that area that you're multiplying a moment arm with, is 0. There's no area above this point away from the neutral axis, therefore it's 0, therefore Q is 0. Finally, our fourth potential type of stress is our torsional shear, and that's going to be maximum again at point B. And at B, it's going to be going in the z direction. So we're on our x face up here at the top. It's going to be going to the right, so going in the negative z direction, because our torque we found is going to be rotating around this way if we're looking up at our cross section. We're on our x face going in the z direction, gives us tau xz at point B. And then our torsion formula then is that torque times our distance, which again is our radius, so c, 600 times 0.5. J is pi over 2 r to the fourth. We get tau xz at point B is 3.056 KSI. So that's our combined loading. Now let's look at it on a stress element. So here I drew our x-axis in line with what we had up here. So it's going down here. And I just labeled it sigma x is equal to sigma b there. It's compressive, 1.019 KSI. No normal stress in the other direction. As is typical for all of our combined loading problems in this class, you're only ever going to have a normal stress in one direction at a point. Now for our tau xz, this arrow here is what I based our shear stress direction on, because we were looking up at our cross section here, and our shear stress due to that torque was going to the right. So this is like looking up at that point, up at that cube, so it's going that way. So tau xz is a negative 3.056 KSI. But again, with these, don't worry too much about it, because we're going to get our same values here for sigma 1 and 2. We might just get our angles off by 90 degrees, but it's not a big deal. Now we can do our Mohr circle to find our principal stresses and our max in-plane shear and the angles. So our center, again, is going to be the average of our two normal stresses, which is just going to be this divided by 2, since that's 0. So we're at negative 0.509, comma 0 is our center. We're always on our sigma axis. Sigma is positive going to the right. Tau is positive going down. And then our reference point here, point A, is sigma x, comma tau xz. So negative 1.019, comma negative 3.056. From there we can find our radius from the square root of the sum of our squares of these legs here from this right triangle. So it's going to be the negative 1.019 minus a negative 0.509 to get us this base of the right triangle. And then the height is our tau xy. Calculate that. Your radius is pretty close to what your tau xy is, because that's your dominant value here under your radical. So your radius is 3.0979 KSI. To find your principal stresses, just add that radius to your center. Get sigma 1 is 2.59 KSI. Sigma 2 is negative 3.61 KSI. And your max in-plane shear is your radius, so that's 3.1 KSI. Okay, so here's tau, here's sigma 1, here's sigma 2. Then to find your angles, since you're over here in the third quadrant, I would just calculate 2 theta P2 first. That's what I did here. Take your inverse tangent of your opposite over adjacent of that right triangle. So that, and then don't forget to divide by 2. You get theta P2 is equal to 40.3 degrees. Okay, this is the right triangle here sketched again, so you can reference it. That's this here. Right? If you know theta P2 is 40.3 degrees, we can subtract 90 from that to take us 180 degrees around our circle to sigma 1. So that'll give us theta P1 is equal to negative 49.7. And then from sigma 2 to our tau max in plane, we're rotating 90 degrees on our circle. So that's a further 45 from theta P2. So theta S1 is going to be 40.3 plus 45 degrees. You get 85.27 or 85.3. Here I also found theta S2 from this triangle. Inverse tangent of this opposite over adjacent is going to give you theta S2 is a negative 4.73. You can see that 4.7 plus 40.3 gives you 45, which matches up with the 90 degrees that we're going from our negative max in plane shear to our sigma 2. Or you can look at it from your first principle to there should also be 45. So this is how if you find one angle, you can get the others. Or what I would suggest is do it a couple times, make sure you calculated it right, compare your values, make sure they're related as they should be, according to your circle and according to our elements, just like this. So this is our max in plane shear element. This is our principal stress element. Right, on our principal element, we only have our normal stresses, sigma 1, sigma 2. If we're rotating from our x-axis to where we have sigma 2, which is rotating theta P2, then our x prime is going to be at sigma 2. If we go a further 90 degrees in either direction, we're going to be over at sigma 1. Okay, you can keep going around too. Another 90 degrees, it's going to take you 180 degrees on the circle. That takes you back to sigma 2. For your max in plane shear, when we're at our max in plane shear here at this point, our normal stress is always this sigma average because that's our center. Okay, we're straight down from our center point. So on each face, we have this compressive sigma average. If we're rotating to theta S1, we're going to have a positive shear stress. If we rotate theta S2 on that face, we're going to have a negative shear. All right, so these elements basically always look the same, just your normal stresses are either going to be compressive or tensile, and of course the angles that we're rotating from and to, the angles that we're rotating to get to our different maximum stresses are going to vary, but you can always label them appropriately. So I also labeled theta P1 here, as well as this theta P2. You can label theta S1 and theta S2. So I think that's 5 or 6 Mohr circle problems we've gone through. So you should be good to get through your homework by now. If not, ask me some questions in class, send me an email, and seek out more help if you need it. All right, I'll see you over at the last set of Chapter 9 lecture slides.